Hmm. Good afternoon, all. Welcome to the sixth week of discussion session of course Plates and Cells offered by NPTEL. The course instructor of this course is Professor Sudeep Talukdar, and I am your teaching assistant. Myself, Asif Prada. I am a PhD scholar from Department of Civil Engineering, IC Bangalore. So today we'll be discussing most of the questions relevant to assignment number 4. So let's start. So the first question is the solution of axisymmetrical bending of circular plate is usually done in polar coordinate system, right? So if a point is located with polar coordinates as P, R, Q, then the expression for del theta by del y becomes. So to solve this, uh, so in polar coordinate, how do we take it? We have x equal to r cos theta and y equal to r sine theta, right? So this would be actually theta. So x equal to r cos theta, y equal to r sine theta. This has been taken from x square plus y square equal to r square, and tan theta is equal to y upon x, right? To make it more clear, we have x and y. We have point P, which is represented by r theta or xy. So this is my theta. So we'll get, if this direction ex and this is ey, so this would give me er and this gives me e theta. Let's do it. So we have this x square plus y square equal to r square and tan theta equal to y by x. So this tan theta, so use this equation, differentiate 2 with respect to y. We get sec square theta t dou theta by dou y equal to 1 by x, right? Which is equal to dou theta by dou y cos square theta by x, and 3 4 from 3 we have dou theta by dou y equal to cos square theta. X is r cos theta, so we get cos theta by r. So our answer would be option number B, cos theta by r. Now let's move on to the next question. The operator del operator in rectangular coordinate system is expressed as ex del by del x plus ey del by del y, where ex are the basis or the directions. The same operator in polar coordinate system is written as, we have this, where er and e theta are basis. So how do we solve this? So we have, as I drawn earlier, so this is my ex, ey, and we have er, e theta at certain theta. So how do we get this? Okay, so we have er as cos theta ex plus sin theta ey, right? And e theta as minus sin theta ex plus cos theta ey. This can be seen as we took x equal to r cos theta and y equal to r sin theta. So since ER theta are unit basis vector and ER points to the direction we take at any point. So if we take r equal to 1, we'll get as x equal to cos theta and y equal to sin theta. This would help me to find ER, right? So now this can be written in terms of vector cos theta sin theta minus sin theta cos theta x ey. When we transpose it, when we take it to the left hand side, we get ex ey as cos theta minus sin theta cos theta sin theta cos theta er e theta. So we have one thing over here, let it be, and the last we had till 4, so let it write like 5. Okay, so this is one thing. Second thing, okay, so earlier we got the value of del theta by del y as cos theta by r. Similarly, we can find del theta by del x, del r by del x, and del r by del y. So if we solve this, del theta by del x, we'll find minus, here we'll get minus y by x. If you want to solve this, okay, we have x square plus y square equal to r square and tan theta equal to y by x. So we got del theta by del y as cos theta by r. Del theta by del x will have sec square theta, that will be cos square theta. This will have minus tan theta by r, and we'll get r. We have x. Is this del r by del x, we'll get 2. Okay, let's solve this. Derivative of this will give me 2x with respect to x. 2x equal to 2r dou r by dou x. This gives me dou r by dou x as x by r, that is equal to cos theta. Similarly, dou r by dou y will get y by r, that will be equal to sin theta. So this we have this cos theta, this is sin theta. Okay, let's solve this, make it more clear. Sec square theta dou theta by dou y, dou theta by dou x is equal to minus y by x square. So this becomes equal to theta by dou x is equal to, we substitute it, this is r sin theta, that is r cos theta whole square, and here we'll get cos square theta. So cos square theta cancel out, so we get minus sin theta by r. This is minus sin theta by r. Okay, so we know when we find a total differential, like if you find a total u which is a function of x and y, when you take a total differential we get dou u by dou x dx plus dou u by dou y dy, and this is again a function of r and theta. It can be written as dou u by dou r dr dou r by dou x plus dou u by dou theta by okay, so this can be written as dou u by dou r by dou x plus dou u by dou theta by dou x dx plus dou u by dou r by dou y plus dou u by dou theta by dou y dy. So this is equal to dou u by dou r by dou x is my cos theta, and this is dou u by dou theta by dou x is minus sin theta by r dx dou u by dou r by dou y is sin theta dou u by dou theta by dou y, dou theta by dou y is cos theta by r dy. So this, if we see dou by dou x as coming out to be cos theta dou by dou r minus sin theta by r dou by dou theta, and dou by dou y as sin theta dou by dou r plus cos theta by r dou by dou theta. So we have delta operator as ex del by del x plus ey del by del y, which can be written as, we have ex from equation 5 as cos theta er minus sin theta e theta, and dou by dou x from 6 as cos theta dou by dou r minus sin theta by r dou by dou theta plus ey, which is sin theta er plus cos theta e theta, and dou by dou y as sin theta dou by dou r plus cos theta r dou by dou theta. So when we simplify this, we'll reach out and get as er dou by dou r plus e theta by r dou by dou theta. Hence the solution would be option C. Okay, now let's move on to the next question. Okay, so the operator delta square, which is Laplacian in rectangular coordinate system, is given as del square upon del x square plus del square upon del y square. The same operator in polar coordinate system is written as So okay, so earlier we got mm, okay, so earlier we got del by del x, like the last one. Del by del x has cos theta del by del r minus sin sin theta by r dou by dou theta, and dou by dou y as cos theta, sorry, sin theta dou by dou r plus cos theta by r dou by dou theta. So this can be written as dou square by dou square can be written as cos theta dou by dou r minus sin theta by r, putting on some cos theta dou by dou r minus sin theta by r dou by dou theta. So this gives me this operates on this, will get cos square theta dou square by dou r square, and with respect to r, so the theta part will be dou by dou theta, and when we get to this, that will be minus 1 upon r square, so this would be r square, and we have dou by dou theta. Now for the second part we have okay, we left it out here, it is dou by dou theta. So with respect to theta, only the first term is there, so that will give me minus sin theta, whether overall will have plus sin square theta r dou by dou r, and with respect to theta, the first term. Okay, so we get, okay, so this would be two terms. First the theta part. Okay, so let me take this minus sin theta by r times 1 upon, okay, this could be complicated, let me write it properly, dou by dou theta of, this is minus sin theta by r dou by dou theta, this is cos theta dou by dou r square plus cos theta sin theta by r square dou by dou theta plus sin square theta by r dou by dou r minus, so the first sine term will give me cos term, so this becomes sin theta cos theta by r square dou by dou theta plus sin theta sin square theta by r square, the theta term, that is dou by dou theta whole square. Correct? So this gives me this. Take it as equation number. So now dou square by dou y square can be solved similarly, like sin theta dou by dou r plus cos theta by r dou by dou theta, operating on the same sin theta dou by dou r plus cos theta by r dou by dou theta gives me sin square theta dou square by dou r square plus sin theta cos theta sin theta cos theta, this will be minus r square dou by dou theta. Okay, now this one, so this gives me operating on R cos theta. Okay, there is one mistake. Here it will be one more term. See, this theta operates on this theta will operate on this, and this will give me two terms, and this will have one more term. Okay, so we have one more term as minus sin theta cos theta by r dou square dou theta dou r. Okay, so that means we have one more term minus sin theta cos theta by r dou square dou theta dou r. So similarly we'll solve cos theta by r. Okay. So let's do this thing all over again. Okay, so we have dou square into x square as operating on this gives me cos square theta dou square by dou r square. Then for this dou r operates on this r and this dou theta. So first let it operate on r will give me minus that will give me cos theta sin theta by r square dou by dou theta, and when it operates on theta that will give me cos theta sin theta by r dou square dou r dou theta. Okay, now this one, in this term minus sin theta by r, it operates on dou by first on cos theta will get minus sin theta dou by dou r. Okay, and then when it operates on r will get cos theta dou square dou r dou theta, right? Similarly the second term, so will for r for theta it will give me plus sin cos, so this give me sin theta cos theta by r dou by dou theta, and sin square theta by r square dou square dou theta square. Okay, this is equation 7. So dou square by dou square, similarly we will solve this thing. Dou square by dou y square is sin theta dou by dou r plus cos theta by r dou by dou theta operating on sin theta dou by dou r plus cos theta dou by dou theta gives me sin square theta dou square by dou r square plus sin theta operates on only can write cos theta by r dou square dou r dou theta, and when it operates on it gives me minus sin theta cos theta by r square dou by dou theta with respect to In the second term, this will get cos theta by r. It will be with respect to theta, it will be cos theta 2 by 2 r. Cos theta by r. So that will be sin theta 2 square 2 r dot theta, and again it will be cos theta by r. So with respect to theta, this becomes minus sin theta. I'll take this one as out, cos theta square. So with respect to this become minus sin theta, minus sin theta 2 by 2 theta, and cos theta by r square del square by del theta square. So now we want to find del x square by del y square. This will be, when we add this, let's match it on. We have this one and this one, which will result in del square by del r square. Okay, now the dou by dou theta term, so this is plus, this comes in minus, so this will cancel out, and dou r by dou theta, this is in minus, this is in plus, this also cancel out. Okay, this gives me dou by dou r term, so this will be, okay, plus sin square theta by r, this would be plus sin square theta by r dou by dou r, this would be plus cos square theta dou by dou r. So this will result into 1 by r dou by dou r. Okay, now minus sin theta cos theta by r square dou r by dou theta, so this cancel out with this, and plus sin theta cos theta dou theta, so this cancel out with this, we'll get for this term as 1 by r square dou square theta square. So compare it with the options, we'll have the final answer as okay, so dou by dou r square is in everywhere, 1 by r dou by dou r is in option second. Okay, so option B is the correct answer. Now the fourth question: if radial displacement in a circular plate subjected to symmetrical bend loading with respect to vertical axis of symmetry through the center of the plate is expressed by this function, then strain in tangential direction at any point distant r from the center is. So this is quite simple, you just need to find epsilon theta, which is given by this relation u by r, as you have all studied, and u is given as ak r k plus 1 k varying from 1 to r and by r. So when you take it inside, it just reduces into ak rk. So correct answer would be option C. Quite simple. Now fifth question: a circular plate of radius A circular plate of radius 10 mm and of radius 8 thickness 10 mm of radius 800 mm is simply supported along the boundary. The maximum deflection should not exceed 2 mm, and the material parameters are given as this. The total load that the plate can support in kilonewton we need to find. Okay, so to solve this, given we are given with thickness as radius as 800 mm and W max as 2 mm, E as 200, GP Poisson's ratio is 0.3. Okay, so this we can find the stiffness of the plate as EHQ 12 minus mu square, which is which on substituting will give me 8.315 into 10 to the power 6 Newton. Okay, this is equal to 2 into 10 to the power 5 Newton per mm square. Now for a plate where the edge, for a circular plate where the boundaries are simply supported, the maximum and there is a UDL, the maximum deflection is given by the relation Q A4. This you can find in module 4 lecture 2. A4 e to the power 4 64d 5 plus nu upon 1 plus nu. Okay, so we are given with the W max, so this we need to find Q. So W max D 1 to the power 4 plus W max is 2 18 64. This is 1 plus 0.3 e to the power 4, that is 800, and this is 5 plus. Solving this, we'll get the value as 1.40386 into 10 power minus 3 Newton per mm square. This is my Q. Now we need to find the total load that this plate can support. So the total load Q will be this UDL times the area of the square, that is pi a square. So okay, so this is 1.40386 into 10 to the minus 5 times 5 times A is my 800 mm square. So when we solve this, we'll get 2.83 kilonewton. So this is my answer. Okay, let's move on to the next question. There is a circular plate of thickness 10 mm, 10 mm, radius 600 mm, which is clamped along the boundary with the material parameters 200 GPa, a Poisson's ratio is 0.25. The deflection under the load P equal to 4 kilonewton in nearest. So, point to be kept in mind, this is a concentrated load, which is 4 kilonewton, and here it is a clamp. So, it's clamped along the boundary with thickness at 10 mm, radius as 600 mm, 200 GPa, it says 10 to 5 Newton or megapascal. So Newton per mm square. Nu as 0.25 and P as 4 kilonewton, which is 4000 Newton. Wait. So if you see the in module for lecture number 3, W max is given by the relation P A square upon 16 pi D. Right? So D is what? P H cube at 12 1 minus nu square, which is 20 to 10 power 5, which is 10 to the power cube 12 1 minus 0.25 square. So if you substitute all this thing, 4000 A square is 600 16 pi, and the D value is 100. It's equal to 2 10 power 8 6 1 minus 0.25. This is equal to 1.77 into 10 to the power 7. Okay, so when we substitute the 1.77 into 10 to the power 7, we get the maximum deflection as 4600 this comes out to be 1.618524 mm. So to nearest two decimal places, so it can be reduced to 1.62 mm. So this is my answer. Okay, so the next question. So this is a set of questions we are given with this figure. Question says a circular plate of radius A has a concentric hole of radius B. Only a small portion of the load symmetrical about the axis of rotation acts on the plane. This figure, the shear force at R equal to 250 mm is 0.05 kilonewton. So let me make it the plan of this figure. It's like we have a radius A with a hole inside with a radius B, and the loading portion is this. So this is B, this is C, and this is A. Now, so what we are given with A equal to 400 mm, B equal to 70 mm, or I can write is 0.4 meter, 0.07 meter, C as 180 mm, that is 0.18 meter. So the shear force at R equal to 250 mm is 0.05 kilonewton meter. We need to find the uniformly distributed load Q in a rounded off to 2 decimal place. That this here, what is that Q value? So at a distance, what do we know? At a distance R equal to 250 mm, we know the value of shear force. So using the vertical equilibrium, that is considering the vertical force of equilibrium, we have that at 2 pi r qr, qr will get, we have, okay, so let me get this. R is 250 mm, which is 0.25 meter, and qr is 0.05 kilonewton per meter. So 2 pi r we need, and to maintain this we get 2 pi r square minus c square, right? So this UDL will be given as 2r qr r square minus c square, that is 2 into r is 0.25, qr is 0.05, r square, r is 0.25 square minus c is 0.18 square. So this is 2 into, so this is equal to 0.83056 kilonewton per meter square. We have to round it to 2 decimal places, so it's equal to 0.83 kilonewton per meter square. And so okay, the deflection of the plate is to be found by integrating the following differential equation. This, the correct symbols bearing their usual meaning. The solutions are to be obtained in two regions. These regions are, so this is quite simple. As we know, del 4 W is equal to QD, or in this case this is the reason, so it depends mostly on QR, and QR in this case varies in two regions as from 0 radius r equal to 0 to first is the loading condition at C, and then from C to A, right? So the correct answer would be 0 to C, C to A. Yeah, the option C. Now the last question of today's session: the deflection of the plate in unloaded portion can be expressed. So unloaded portion is from 0 to C. Okay. So first, here we use this relation that d by dr and r d by dr r dr. No, dw by dr equals to minus qr by d. Okay, so it's confirmed. Now solve this. So for this unloaded portion, that is 0 to r to c, we have qr equal to 0. So our expression reduces to 1 by r d by dr r dw by dr equal to 0. Okay. Now integrate this relation on both sides. Integrating on both sides. We get as 1 by r d by dr r dw by dr as some constant. Let me write it as c1. So this becomes d by dr r dw by dr as c1r. Now again integrating on both sides. We get r dw by dr as c1 r square by 2 c2. Okay. Now this again can be simplified as dw by dr as c1 r by 2 plus c2 by r. Now integrating again. With respect to r. We will get expression of w as c1 square by 4 plus c2 of this. We get log r plus c3. Okay. So this c1 by 4 can be written as a, c2 as b, and c3 equal to c. So expression reduces to ar square plus b log r plus c. So this is my final answer. So correct answer would be ar square by 2 b log r plus c AR square T log R plus C. So first term. Okay, so this is all for today's session. If you guys have any doubt in today's session, please to ask. Yeah, so we'll end the session today over here. Thank you all.